Hello everyone, welcome back. We'll be handling our chapter 7 on thrusters, another attitude actuator, which is very important as well. Not only to do attitude control but also orbit control. We'll discuss a bit on how it's going to work. More importantly, please understand that Euler equation of motion, the linearized Euler equation of motion, still is applicable to this actuator. We have discussed quite a bit or quite lengthy sessions that we had regarding those equations, and you have also seen how we have brought in the rotational motion attitude actuators, for example, reaction wheel and momentum wheel, how we can actually embed that into the equation of motion. And today I'm going to also demonstrate to you how are we going to embed this actuator, basically the thrusters, into the actual equation, so that we can practically have or define a control loop to control this particular actuator. Now, as far as that the control system is concerned, it is practically it is another actuator for the control system. So, which means that if I have a control system, I think clearly explained to you in the previous chapter with the rotational control, with the reaction wheel and momentum wheel. If we have a control system, and that actuator, we can have the same control system. We take out that actuator and put another actuator. Technically speaking, you should be able to actually work with that. So the control system are not very sensitive towards to the actual actuator. More importantly is that the choice of the actuators that you want to be choosing depends on the application cost. So let's see first. Now, just a reminder. I think you should have done this in satellite technology, whereby there's one of the particular subsystem that you would have been exposed to is a propulsion system, or even the thrusters. In satellites, we call it thrusters. We don't call it a satellite engine. We call it thrusters because it is a propulsion system. Typical ones, basically, you have a cold gas, hot gas, and electrical propulsion. Basically, you have. If you see that the options that actually we have, for example, hot gas, quite typical example. You have, for example, bipropellant. You have oscillator. You will have the fuel, and here you have unsymmetric monomethylene hydrazine and N2H4 nitrogen tetroxide as the actual oscillator. So these are quite very typical. I think you have been exposed to. So there are many options that how the system is going to look like. But as far as the control system, we want to actually know that there is an actuator, and we just want to actually model the actuator, and so that our control system actually can respond to that actual attitude corrections that we want. So that's about it. So for us, is that it's fine. You want to use in satellite technology, you would have been actually exposed to what are your options that you have. Thrusters, what kind of thrusters is available. So in what mission actually you want to use these thrusters, and another mission maybe you want to use another thruster. So how do you want to do the selection? That is going to be a satellite technology. But in spatial dynamics control is more into actually how am I going to control this actually thrusters in order for me to get a torque, for example, right? Now, go on. If you can remember clearly. In the previous chapter, we have actually modeled the reaction wheel, okay, or even the momentum wheel. My control loop remains the same. This is satellite dynamics. We will discuss a bit, maybe in the discussion. This is a satellite dynamic. This came from where? This is we have actually said this. Okay, fine. This is going to be maybe, for example, maybe the pitch axis, and we say that this plan actually came from where? Came from the actual derivation that we have done using equation of motion, Euler equation of motion. We have linearized it. Then we have actually established the plan for rho yaw dynamic. For example, this can be the let's say your pitch, for example. And you have a modulator. This modulator, and you have basically modulator plus the actual controller. For example, you can assume that this is going to be your controller, and K here would be the actual constant with respect to the exact actuator. So assume a very perfect actuator. Let's say you need 1 Newton. The propulsion system is going to give you also 1 Newton. It produces perfectly what you ask. Then this can be 1. Otherwise, and it is super fast. That means you ask for 1 Newton now, it gives you now 1 Newton. So it's a super fast. So technically speaking, what you requested and the actuator is providing that amount. So this is a actuator's model actually. So when a perfect actuator, then you can say this is 1. So technically it is going back to the same control loop that you have been exposed to in the previous chapter of reaction wheel. You have a plant, you have the wheel, here is wheel or even the actuator, the propulsion system, and you have the controller. Okay, how it does? Difference is that we don't operate thruster system or propulsion system in satellite throughout the mission. No, when we need, we operate. Unlike the wheels, reaction wheel we operate throughout the mission. Once you on, you don't switch off because that's the active motion. So here we don't use it like that. Okay, we when we need, we on. So it's always an on off. Okay, on off. Then technically you will have the delay. If you have a delay, then it's fine. But if you don't have a delay, then this should be a perfect. I would say a perfect system. So that depends on the actual model of that exact thrusters that you have. Okay. Now, if you don't have any delay, let's say, so technically speaking, what you have given out, quickly you measure. Okay. So this is a sensor basically. So you do the sensor model. This you say okay. Sensor model is super perfect, and whatever I give out, I measure. Then quickly I can compare to what they have. So this is a typical loop. Right? This is for the propulsion system, and this is very similar. In fact, I can say it's the same with the reaction wheel. So on. Now this is a Wacom solution. This is just to combine to tell you how I'm going to actually now combine my thrusters with whatever you have learned. You have learned basically a pitch momentum wheel. You have learned in the previous chapter. So I'm going to do that. I'm going to now, instead of using the reaction wheel or instead of using magnetotorquers, I'm going to now use thrusters. So therefore, let me define first. Assume this is a cylindric body, rigid body. Along just like what I've learned before or what you have been exposed before, I embark my momentum wheel along the pitch axis, and this is my pitch axis, and you can see that it is being embarked. Okay, and then I will have my roll and yaw. Okay, roll and yaw axis here, and I would say that these two you got to zoom. Then you can actually read this clearly. So you will have these thrusters. So now again, please do there are two thrusters here. These two thrusters are actually in charge of the actual body, actual pitch. So remember, I told you when you have a momentum wheel, when it goes, let's say you want to use it for attitude control also. So what exactly happened? The speed build-ups. So when the speed build-ups, actually you need to dump the wheel. That we have learned. So in order, we've been using magnetotorquers in the last chapter, but you can use also the thrusters basically to dump the wheel. Means that I give a negative torque so that the wheel speed is going to actually slow down. So in order for me to get a negative torque, I have to actually have, let's say this is a cylindric body. I fire thruster system. I fire, let's say 1 Newton up and 1 Newton down. This body is going to rotate. So depending on a positive or negative rotation, you can actually have a rotational motion in order to set the wheel. So this is basically a thruster system which is in charge to desaturate the wheel, the momentum wheel. But for my control, what I can actually have a control practically with this motion, this thrusters, technically speaking, I should be able to have a rotational control for the other two axes. So that is why you see here the pitch momentum is minus hy. H is momentum, angular momentum, okay, hy. So it is going to be a negative of pitch, yes, of course, because the momentum will, if you look at it, momentum will up, there is a positive, but your pitch is actually down, just like what you have been exposed to in the last chapter. So it is actually negative, same, okay. The only thing actually I've introduced today is this thruster torque. Basically, I can say that the thruster torque would be is the angle, a cosinus angle or sinus angle of that particular configuration. Now, why this design? Remember, the thrusters can be also used for translational motion. So there is a design consideration that these thrusters can be also used not only for attitude but also for translational motion. You can use this for translational motion. So when you can actually do that, so technically speaking, the actual direction of the actual thrusters, the divergence that you see here, is very important. So in order for us to have that, and plus it can actually help us to control the exact attitude for the roll and your exact amount of thrust that actually you have, for the top you have, is basically the actual tilted angle of the divergence or the thrusters that you embark. Now, sometimes you don't even have to have this. It's fine, no problem. It depends on where you embark. For example, this Wacom solution, there's an angle. Okay, not necessarily every time you mustn't have angles. For example, here, you don't have an angle. You don't have an angle. In a pitch axis, you don't have an angle. It's a straightforward saturation. That means, so you don't have to. So, what it says that, look, in order for me to have a 3-axis control, I have pitch momentum taking care and giving me a gyroscopic stiffness, just like in my previous chapter. Plus, when I have a pitch momentum and a pitch angular momentum, pitch angular momentum wheel, I should be also be able to take care of the pitch axis attitude. Done. Pitch is done. Now roll and yaw. So when you roll and yaw, if you look at it, okay, your roll, I have a thruster, and my yaw can be also managed by a thruster. So it's very simple. So I have two actuators here. I have a thrusters, I have the momentum wheel, I can do 3-axis control. That's what it means here. Controller, this is the same PD controller that I have used to control the wheels that you have done, that wheel that you have been exposed to. Go on. Now, this is a bit interesting. You look at it. Assume there is no tilt. There won't be any. Here, this is the important. Assume there is no tilt. There won't be any cos angle here. It will be directly. That means 1-to-1. My PD controller, just like for your wheel, same example. Okay, here is what actually is a bit interesting. Now, remember this. This is the same equation that we have developed, and you have been using. This is with gravity gradient torque. That means what? Remember the gravity gradient component that we have inserted. This is including the gravity gradient component and with a wheel. And so H dot will be a torque. Momentum will torque. So which means that my pitch axis here can be controlled by my wheel. That means I increase the speed of that momentum wheel, I should be able to have a torque. Okay, again, remember all those disturbances will be on your right side. So there is a disturbance here actually. I didn't write, but actually you will have that exact disturbances. Okay. So let's say I move that pitch axis. Let's say I move this torque. Control torque here. Here will be plus H dot, and this is a torque. So this is an internal control torque. you plus, actually you minus, you have to minus that external disturbance torque. So it will be 0 always. It will be always 0. Okay? Who is going to give you the torque along pitch axis is the momentum wheel is going to give you the torque. Okay, done for the pitch, roll and yaw. Same. I need a torque. And who's going to give me the torque? My torque is going to be given by my thrusters here. So the thrusters equation is here. This is actually the torque which belongs to the thruster. Okay, let's say this is plus. There should be minus external disturbance torque. And let's say there is a minus, let's say 0.5 Newton meter external disturbance torque. I should give, that means the thruster should provide me plus 0.5 Newton meter torque. So both will be a net zero. When there is a net zero, nothing will disturb the set line. That's what it says. Okay? So I need to provide this. How can I provide this? I go to this control block. Okay. Please look at this. This is basically just the same exercise, or rather same approach that I've taken, where I analyze the roll-yaw coupling in for the wheel, for the reaction wheel or even the momentum wheel. Same. Inertia, basically you have this is for your roll dynamics, and this is your yaw dynamics. Okay. So what exactly it does here? If I control, because both of this roll and yaw is coupled, so I say that okay, never mind. I'll make sure I measure roll, then indirectly I am also controlling my yaw. That's what it says here. That is the reason you don't see a closed loop for the yaw. That means I measure roll and I indirectly can control my yaw, because roll and yaw is coupled. But I always have to measure the pitch, because pitch is coupled. Okay? Roll, yaw coupled exists, pitch is decoupled. Just like what we have been always doing. Now let us see. So the explanation for this is very easy. When I give you all these numbers, I mean all these parameters, you should be able to actually put this in a plant, and you should be able to actually calculate this. Again, the standard form, this is a detailed form. The standard form would be again same. Go on before this. Yeah, this one. It will still come back to this. This is the exact plan that you are talking about. Okay, go on. Yeah. This is the exact plan that you have. You will have a second order system. This is practically a second order system, because the equation actually is like that. Second order system. Okay, go on. When you have a control block, you should be able to, you have done in control system, you should be actually able to do a root locus. You can find the poles, and in order for you to select all those, what you want to select, before you go back, what you want to select, you want to select the controller, because the inertia is already known, it's clear, satellite inertia is known, orbital frequency is also known. You want to actually look at the gain, that means the proportional gain and the derivatives gain. How to actually do that? To select that, we do a root locus. For example, you can do a root locus, you can do a board diagram. Okay. So in order for you to find the poles, for you to ensure the system is stable. This is very typical in control system. Now, what exactly is a general active control system for this spacecraft? What exactly is happening is this. Now, this is basically a satellite which comes with the momentum wheel. Alright, done. So what I'm doing is that I'm actually controlling. I got an earth sensor control. I control the roll, the thruster, and the actual torque as it comes in and controls the satellite. And indirectly, I have this thruster. I don't measure. If you look at it, I don't have to actually measure my yaw. I don't measure my yaw. I only measure my pitch. See this? This is the pitch sensor measurement. What you want to measure? You want to measure the attitude. What you can use? You can use a gyro for sure. You can use the gyro to measure. You can use the gyro to measure. So I have only two gyros. and I can measure 3, I can actually control 3 axes. That means indirectly, my third axis is the yaw axis, I don't worry. I control 2 axes, okay? Measure and control. Indirectly, I control my yaw. So, pitch, done. Then my roll is done, sorry, pitch, done. Momentum wheel, my yaw, indirect, indirectly. Okay, so there is this actually also option that you can have. But again, for your project work, you can't have this option because this will be a very expensive option. Yours is going to be quite a low cost option that you're looking at. This will be a very expensive option. You have thrusters plus you have momentum wheel on board. So that's something to ponder. But if you have a huge satellite, you have a very long mission, why not? This could be actually one of the good missions that you have. So what we have actually seen here, a combination of solutions, combinations of actuators. You have gone from a very primitive way of controlling satellite. How? Gravity gradient stabilization. That means at no cost, just playing around with the inertia. Then after that, you have gone into a bit more expensive, which is the magnetotalkers. Expensive in terms of you need to actually power the talkers, you need to have the device. Then after that, no, it's not good enough. If you look at it, it actually gives me a very high amplitude in terms of altitude. And you embark the options of the rotational actuators, which are reaction wheel and the momentum wheel, or and/or. And you have found out that is fantastic. It is giving us a very good results. But other than that, how can actually we use also this, for example, propulsion system? Now remember this, we may have propulsion systems on board sometimes. So how can we use it? Use propulsion system in order to help us also in altitude control. That's how we see this combination of all these actuators. So depending on what you want to do, but remember this, it is this option of controlling the roll via thruster. It is going to be an expensive option because the thruster will be on, and when the thruster is on, the fuel you're going to actually consume. So it is going to be expensive in that sense. So it may not be the best option that you want at the moment because you want to keep the cost low. You may want actually to keep the thrusters either for orbit control, translational motion, or maybe momentum dumping. Yes, it's possible. Yeah. Okay. So let us see this. Go on. Now this is what exactly happened here. Like I've explained. You have gravity gradient stabilized. You have a 3-axis passive stabilization. Now I have if you look at the equation, I have actually gravity gradient. I've embedded the gravity gradient related equations inside in order for me to also to capitalize on that. Well, I would say a low cost method. So after that, I use a bias momentum. Why? Because I embark my reaction wheel, momentum wheel actually. So there's pitch is active stabilization. Okay, I have a controller R2. I can have a momentum wheel basically, and I have an earth sensor. One earth sensor is good enough. This controller can be it controls basically reaction wheel. R2 controller, reaction wheel controller. Okay. Then roll your passive stabilization I have, because why? When I have a bias momentum, we have also seen in the previous chapter, it gives me a gyroscopic stiffness for the roll and yaw. When you have embark your actual momentum wheel along pitch axis. So it's not bad. It gives me a good auxiliary, passive stabilization. Okay. Then what exactly the solution that you have? Pitch. So the actual solution that we have here, pitch is basically active because I have my wheel. Roll is active, I have my thrusters. Yaw is indirect. Okay, yaw is indirect. Smaller oscillation can be actually, well, you can still find a smaller oscillation, but through roll control torques, practically it dampens. So major, because you already have, you're stabilizing it quite well with already the passive stabilization, plus the roll control are going to also help to control the yaw because they are alternative. Remember, so when you constantly control roll, you are also helping to control the yaw in that sense, because it's a coupled motion. Okay, so this could be another variation of usage of actuators, attitude control actuators. Okay, thank you.